Day 2, cold flow, mission control. How's it going?
Hello,
good.
Buddy.
Good. Okay.
Pretty good.
Let's check out the. So who's over there? Jack and Ethan?
Yeah.
All right. I think I'll go over there.
This is true.
All right. I think I'm gonna head over. Is that good?
You got hearing protection on you?
Yeah.
Okay.
Hey everyone. This is cold flow, day 2. Getting a lot of hardware set up. Chilling in tanks. Hello. Do the live stream. We got the engine assembled.
Live right now?
Sorry?
You live right now?
Yeah.
Yeah, so right now we're just doing some preliminary filling of wash tank. It's a low pressure fill, basically prepping the hardware for the actual cold flow. Yeah, that's you see all the insulated stuff is the cryogenic hardware. We have an engine mounted in the thrust stand. We have a camera set up right now being worked on. You see the load cell and main propellant line coming in there.
Aux line going over to the main oxidizer valve right there. Fuel line going over to the main fuel valve.
This is our fill tank. Oxy's on the right, fuel on the left.
Sweet. Liquid nitrogen chilling in. You can see the cool air coming off it, condensing. This is about 70 liters of liquid nitrogen.
Mission control. Can you please read off the pressure on Ox ETFO1? It is the Ox tank pressure tank user.
Yeah, this is the liquid oxygen tank that we are chilling in with liquid nitrogen. Obviously, we wouldn't be over here if it was liquid oxygen. We're also setting up cameras. So, in addition to this view on my phone that I'm live streaming, we have several GoPros that we are setting up to track the fill process. So, what we'll have actually, So what we'll have is, at mission control, we have a computer that will be displaying video feed from 4 different GoPros. So while we're at mission control, we can watch views of the fill system. So here's one view. We got this camera that's going to be looking at the engine setup and the valves and the main propellant tank. And then we have another camera out back. This is the fill system area. This is where our avionics sits. So everyone on camera. So this is the table where the avionics sits. You can see we have the engine controller right there. Let's get a better look at that actually. So this is the engine controller. This is what commands the about the 32 valves that we have on the system, reads data from 20 pressure transducers roughly, and is basically the brains of the engine. So here's Jack setting up cameras for the fill system. This way we can have eyes on the fill system at every moment of the fill process when we're at mission control. So we're over at the bunker right now. You know, this is our bunker. But over there is mission control. You can see behind the barrier. That's where we go when we conduct pressurized operations, things with high pressure helium. This is our high pressure helium bottles. They're strapped down really well. Yeah. And also you might hear some hissing inside the bunker. That's normal. That hissing is actually, so what we're doing is we are feeding liquid nitrogen into the liquid oxygen tank to chill it. So the liquid oxygen tank is very hot right now. It's room temperature approximately. That's very hot for cryogenic liquids. So what we have to do is we feed in liquid nitrogen, and then we feed it in for about an hour, and that cools the tank down. That takes a very long time, and that's the hissing you hear. You hear gaseous nitrogen venting out of the tank quite fast. So you can see right here, these are our these are the lines going into the bunker from the fill system. So that's, and also the helium. You can see this, the helium bottle. We've got a line coming down, coming down into the fill system. Now let's check out inside the bunker again. How's it going, Jared? This is our safety officer. You got our SOP in hand. Like always, you never do anything without an SOP.
Always have SOP.
Oh yes, SOPs are very important. Let's take a look at mission control. Sorry for the hissing. It's actually kind of hard to tell, what's going on with the with all the loud noises. I don't know if you guys can hear me very well when I'm inside of the bunker. Hey. Very good. Oh wow, we have people watching even over here.
Yeah, because I can't see anything through the bunker wall, so this is actually the best way for me to see the inside of the bunker.
Yeah.
Right now.
Oh, awesome. Thank you guys for the comments. So I could hear you just fine, but it's a little hard to hear in the bunker. I'll keep that in mind. When I'm in the bunker, I might just give you guys some cool views rather than talking. So, all right, let's just, this is the view that we get. We got mission control. We got Alex over here on the computer. That computer is running our custom software that is connected to the engine controller, which I showed you earlier.
It's saying 0, but that's because we don't know. I don't know what the initial 0 offset is. Stand by.
It's very hard to see. Sorry for the lighting, guys. It's very hard to see the computer here. I don't know if I can even get a shot of it. Yep, no, you can't see that. Well, we have basically it's the GUI, the GUI that runs the engine controller. That's where we press buttons, we turn solenoids on and off, we read data from pressure transducers. Yeah, and then also in a little bit. So actually, right here. This is the computer that we'll be watching live video from the bunker. So as I mentioned, we have I think 4 GoPro cameras that are set up in and around the bunker that we will be watching live video from while we're doing the fill process, and that's really important to know what's going on. There's some things that data from a pressure transducer can't tell you. For example, if the liquid oxygen tank is getting nice and frosty and covered in ice, from the video we'll be able to tell that it's chilled and full. So there's a lot of important things that video gets us. It's not just video is cool to watch. The video is actually crucial to these operations, so that's why we have that set up. So let's take a look inside the bunker. I'm gonna stop talking because it's really loud in there with the hissing, the venting. So I'll just stop talking and show you guys some cool views. All right, let's go in.
Maybe. This will. We'll be able to use cold gas. Is there any lighter in there? No. So, yeah, I'm not sure if this will be enough or not. Especially because we don't know what the boil off was yesterday.
What was that?
We don't know what the boil off was yesterday. So.
This thing was for a long time.
Yeah. Oh, that's true. It is fine. So that might not be an issue. That makes sense.
Hey Bill, what material is the nozzle and combustion chamber made out of? Let me back away so that you guys can hear me a little bit better. Yeah, so Bill asked what material is the nozzle and combustion chamber made out of. So the nozzle right now is actually a placeholder, basically. We actually have a solid graphite nozzle being machined right now. We have it being machined out of house. Here. You guys can see me. So yeah, we have a graphite nozzle that's being machined out of house. That's going to be a converging, diverging bell nozzle. That's basically to get hooked in on the engine, maybe on like hot fire number 2 or hot fire number 3 in a few months. But right now we have an aluminum nozzle, basically as a placeholder. And you notice it was kind of short. That's actually half of its full length. We decided to just truncate it, make it shorter so that it's easier to machine, less aluminum we need to purchase and lathe down. We did that nozzle on a CNC lathe machine at our Wilson Center facility here at University of Michigan. So yeah, that's the nozzle material. It's going to be graphite eventually. Right now it's aluminum just as a placeholder. And you might ask, does aluminum melt when it's a nozzle? And the answer is yes. That's why we will only be running the engine for about 1 to 2 seconds with the aluminum nozzle. Once we get the graphite nozzle in there, then we can start ramping up the burn duration to get closer to the full 40 seconds, actually about 41 seconds, that this engine needs to burn for to put our rocket into space. And by the way, the rocket we're building is called Tangerine Space Machine. That's what we decided to name it. And that's a rocket to compete in the Base 11 Space Challenge. And that engine you were seeing inside there, locked down on the thrust stand, that engine will produce 3,800 pounds of thrust. That will be the biggest collegiate liquid engine ever built. I think the next biggest one is about 2,000 pounds. Last year we built an engine that was a liquid engine that was 1,000 pounds of thrust, but this year we had to go much bigger to satisfy the requirements of this space liquid rocket. Let's check out the what's going on over here. Oh yeah, and then Bill, you also asked, what is the combustion chamber made out of? So the combustion chamber is made out of a certain stainless steel alloy. It's actually kind of an interesting material selection there. It's hard to go into all the details, but basically it's a stainless steel that that's the regeneratively cooled. That's a regeneratively cooled surface. So basically, on the inside of that stainless steel is combustion gas. About 4,000 Kelvin. That's the heat of the combustion gas. So it's extremely hot. So obviously that will melt if you don't do anything to it. You can't have a metal rocket with no cooling. So what we do is we run the fuel on the outside of the stainless combustion chamber jacket, and that keeps it cool. Thanks for asking the questions. We love to get questions and be able to answer them. Because sometimes we forget, what. Sometimes we forget the things that we've posted on Reddit before, and on Facebook we don't know what's public and what people know, so we're happy to explain things about our rocket. So we got another question. Yes, that is the regeneratively cooled bit. That inner chamber, that's regeneratively cooled. The outer surface, so you have fluid flowing through, the regeneratively cooled fluid, which is actually the fuel. So on the inside is the combustion chamber. That's what it's cooling. On the outside of the fluid, you know, you have to trap the fluid with 2 walls. The outside is an aluminum jacket, and that's actually what you see. So when I was looking over at the engine, you saw the aluminum jacket. You can't actually see the stainless steel on the inside. That's hidden from view. And I think we got another question. What type of injector are we using? So we're using it's a type of plate injector. It's not a pintle, it's a plate, but I'm trying to think. It is I'm trying to think the term for it. It's an unlike impinging triplet injector. Yes, I think that's what it is. So we got another question. Will any of the hardware be used for flight? That's a good question. So what's happening with this is the 3,800 pound force engine we're building. We decided to make it liquid oxygen and ethanol because we used ethanol last year for our liquid engine, so we were kind of familiar with it. And then we decided to do liquid oxygen as oxidizer instead of nitrous. We've done nitrous oxide in the past, but we decided to do liquid oxygen because it has much higher ISP, which is basically required to get this rocket to space. But will any of this hardware be used on the rocket? So the answer is actually probably no, because we will be doing several iterations of this engine. Almost certainly we're going to want to change something, or maybe we want to change everything. With the engine, you know, like the nozzle, the combustion chamber, the injector, the way the injector mounts in, and our main propellant valve. So our main fuel valve that we made in-house, designed and made in-house, our main oxidizer valve that we designed and built in-house. So we'll probably, I would think that none of this hardware in this room is going to fly, surprisingly enough. We're probably going to redesign and rebuild everything at some point. And that's not because we built bad hardware, that's just because we figure out that there's way better designs that we could have. Like, once we design and build this, we realize, oh, this one component is a huge pain to manufacture. So let's not do that. Let's not do that anymore. And maybe this engine is actually pretty hard to build. Once you get all the components, that's only half the battle. You have to put O-ring seals in there and assemble the whole thing. So yeah, we will probably be redesigning a lot of this hardware. And actually, there's a good chance that we're switching to liquid oxygen and RP1 for the rocket. So we're starting some noisy operations, so I'm going to step back so that you guys can hear me. By the way, for viewers who just came on, the noise that you hear, that is liquid nitrogen turning into a gas. And then it's venting out of the tank. So we have a tank right next to the engine that will feed the engine with liquid oxygen for the hot fire. And right now we are chilling that down. We're cooling it down from room temperature to cryogenic temperatures, which is about negative 300 degrees Fahrenheit. So the noise you're hearing is liquid nitrogen going into the tank, instantly boiling off because the tank is so hot compared to liquid nitrogen. And then it turns into a gas and then expands, and that gas vents out of the tank. So that's the hissing you hear. It's pretty loud. I don't really know if you guys can hear me in there when I'm talking, if the venting is happening, so that's why I come out here. And then yeah, I was saying that we're going to be probably switching to liquid oxygen and RP1. And that's the reason why that entire engine is probably going to get redesigned, rebuilt, and tested again. It's actually going to look quite a bit different probably. But yeah, so what we're doing with this engine is this is the first time we've hot fired an engine of this scale, so 3,800 pounds of force. So even though we know this engine won't fly, we have to do a lot of testing on it, and being able to test out our fill system and our avionics and just the way we're igniting the engine, which I could talk about in a little bit. So there's so much to test on this engine, and having a successful hot fire with this. Today we're just doing the cold flow, but eventually successful hot fire will be huge for this whole program and for flying a rocket to space. And then maybe, I'm trying to think, late summer, early fall, we will be building and testing the RP1 engine, which will be a very similar amount of thrust, but just using RP1 instead of ethanol. Let me check out some of the questions. I think some more questions came in. Oh, sorry. Oh shoot, sorry, I think I don't know if I was broadcast. I turned the camera around to try to talk to you guys, but I don't know if it was pointing the other way. Sorry about that. But let's check out some of the questions. So, pure ethanol. We're using pretty much pure ethanol. I think it's 95%. 95% ethanol. The reason is, there's a lot of reasons. It'd be hard to go into. You could write a whole report on it, why we're using the certain ethanol we are, but it's for the things that come into play when you're trying to decide what percentage ethanol to use is how well it is, how well it does at regenerative cooling, how much thermal energy, how much heat it can take away from the combustion chamber and cool off the combustion chamber and keep it from melting. So that's one of the reasons. Another reason is its availability. Getting 100% ethanol is actually really difficult. You have to go to like specialized lab stores, and you have to jump through a few hoops, gotta sign some more paperwork to get it. But ethanol, like 75%, that's a lot easier to get your hands on. And by the way, we're not actually using pure 95% ethanol with 5% water. It's actually 95% ethanol, 1% methanol, and then about 4% water. The reason they put in the methanol is that makes it poisonous, so you can't drink it, because obviously ethanol is just alcohol. So it's selling alcohol is different than selling denatured alcohol, ethanol. So yeah, you can actually see that's the ethanol right there. It's in a closed bucket. Yeah, there it is. It's all sealed up, hasn't been opened yet, so it's fine that it's over there. But all right, let's see. I think there are some more questions. Let me check this out. So pure ethanol. This engine looks smaller than the last year's. Is that true? Oh, okay. So that's actually a pretty good question. So this, what's in there? What I showed you guys in the bunker. What I showed you guys in the bunker, that's just the combustion chamber. So last year's engine, what we posted pictures of it, and what we called the engine was actually the combustion chamber plus the nitrous tank plus the ethanol tank plus the engine controller. It was all in this big vertical stack, and we called that the engine, but really that was like most of the rocket. So this year the combustion chamber is like alone. We have the combustion chamber, and then the tanks and plumbing are to the side. So what you see is the combustion chamber, and like, you know, the injector, combustion chamber, nozzle, which you call the thrust chamber assembly. Some people just call it an engine. So this engine is actually way bigger than last year's. If you compared last year's thrust chamber assembly to this year's thrust chamber assembly, this one is like way bigger. Last year's maybe weighed 10 pounds. This one weighs 30 pounds. It's huge. It's actually very impressive. When we put it together, we were just blown away by how huge it is. So yeah, so that's thanks for that question. Is the engine smaller than last year's? No, this engine is much bigger than last year's. Last year was 1,000 pounds of thrust. The chamber pressure was about 350 to 400 psi. This year, the thrust is 3,800 pounds of thrust. The chamber pressure will be about 450 psi. All right, so another question. Are you guys going to publish your design and report or make it available to the public in some way? Good question. We're not quite sure on that. So what's kind of interesting about the team this year, like versus past years, is in past years we were trying to be like kind of like secretive almost. We were thinking, oh, we don't want to like, you know, divulge our secrets and divulge our designs and hardware to other teams, because they might use those designs and then beat us in the competition or whatever. But this year we kind of decided that was silly to try to be secretive. Like it does no good. It doesn't help the rocketry community to be secretive. It doesn't even really help us, because like people don't actually like steal entire designs, and even if they did, you know, who cares? Whatever, they can take our design and build it. That's fine. I mean, you know, more the merrier. More people launching liquid rockets, the better. So, you know, if you guys get inspired to, by one of our designs, like say our propellant valve or the way we're doing our injector, you know, that's great. You're able to be more successful with your own project, so that's awesome. So this year we're getting in more and more into posting, you know, we're being more comfortable with like posting pictures on Reddit and Facebook, like up close pictures of our hardware that it really gives out a lot. You can tell a lot about our design based on the pictures. But we haven't quite gotten to the point to publishing our reports, because the reports actually have everything in it. Like if you read our report, you could replicate our engine, because in our reports we have the engineering drawings, so you could just take those drawings and machine them. And in the report, it tells you how to assemble it too. So you could build that same exact engine based on a report. So we haven't quite gotten to that step yet of like being open source rocketry. We haven't quite gotten to that point yet, but maybe in the future that's something that we'll do. We actually just submitted our phase 1 report for the Base 11 Space Challenge. We submitted that on Thursday night. That it was due on Friday evening. So that is the end of the first phase of the competition, which is preliminary design. We've actually been doing a little bit more like critical design and building components and testing them. And so yeah, that's our report. But I don't know if we'll publish the phase 1 report in the near future, unfortunately, because it gives away so much. It tells you exactly what we're doing and exactly how to build our hardware. So we're not quite ready to be that open with what we're doing. But we are trying to be more open and show off what we're doing, because it's really cool. We love showing you guys like what we're doing. So that's why we had this live stream. We didn't used to do live streams. This is the second time we've ever done a live stream. The first one was yesterday. So yeah. Let's check out. We're here. You don't want that fuel vanishing mysteriously. yeah, the fuel is denatured. You cannot drink the fuel. If you did, you would die. Oh, so Stefan asks, if you guys are trying to get a rocket to space, have you thought about launching it from a hot air balloon? That's a really great question, Stefan. And actually, to tell you, we're switching over our rocket to be a balloon. We're actually building a balloon now. Yes, we're building a balloon. A high-powered balloon with side balloons, with a staged balloon system to get our.
The inside the liquid and outside the liquid solid, so they're just blocks machined into the shape of a balloon.
Yes.
Yes,
we have a balloon system now to get to space. That's satire, by the way. Thanks, Stefan, for the question, but no, we're not using any balloons. Oh yeah, post more pictures and reports on our Collegiate Rocketry Slack group. Yeah, we'll have to do that. It's really cool to show off pictures, and I'm glad that you guys are following it. Yeah, so who designed your injector? It looks pretty impressive. I don't know if I want to start naming names, but yeah, we have a really awesome group of people who do our propulsion design. I don't know if he's watching right now. He might be watching the live stream right now. But yeah, we had a member design it last semester, and then it got machined towards the end of last semester. So yeah, so let's check out actually a more up-close view of the fill system. It's actually pretty cool. So here's a camera. This camera is going to be, videoing the fill system during, like, when we're doing like hazardous operations. So when things get hazardous, which is when we're pressurizing tanks to high pressure, and really anything above 100 psi, and when we're starting to flow volatile fluids, so when we have the ethanol in the tanks, when we have liquid oxygen in the tanks, we go over there. We go to mission control. We leave this area. We don't stay over here when we're doing stuff, and especially when we fire the engine. When we fire the engine, everyone is over there at mission control. No one's over here. It's dangerous, so we make sure that we have at least 2 walls between us and the engine. So we have the wall of the bunker, then we have the wall over there that we huddle behind. So we make sure to do this stuff safely. All right, trying to think some more questions. Yeah, so thank you for the comment. It is a very impressive injector. It's really cool. All right, what type of ignition method are we using? I can show you guys our igniter. What our igniter is it's a chunk of APCP, which is basically solid propellant. That's what a lot of solid rockets use. APCP, ammonium perchlorate composite propellant, and it's basically like a chunk, like this big. Maybe it's like a cylinder, like this big. And we put it inside of a styrofoam cup, because the igniter we want the igniter to be like insulated from the liquid nitrogen. It's actually pretty complicated. Like, it's a pretty complicated problem we had to solve with a really easy solution. So the igniter is right by the injector. That's where it sits. It's stuck there. We like fasten it inside, and then we fire the engine. The igniter goes off, and then it ignites the propellants. But we chill the injector with liquid nitrogen before we fire the engine. But the igniter is in there. So the igniter is sitting in the combustion chamber, and we're chilling the injector by flowing liquid nitrogen through it. So that means the igniter is getting doused with liquid nitrogen. And you might think, will a frozen solid chunk of propellant still catch fire? And the answer is no, not always. It has about maybe 50% reliability when it's frozen. It'll light half the time and it won't light the other half. So we thought we have to get this igniter to not be frozen when we ignite it. So what we did is we decided to put it in a styrofoam cup. We cut 2 styrofoam cups in half and sealed the igniter in there. So it's this like styrofoam capsule. So the liquid nitrogen doesn't go inside the styrofoam cup. It's insulating the igniter from it. And then when the igniter goes off, it melts the styrofoam in like a quarter of a second, really quickly. And then the propellant flows in, it ignites it. So we've done tests of our igniter, but we can go check out what the igniters look at. They're over there by our hardware. Oh yeah, can you comment on the mass flow rate of propellants this year versus propellants last year? Thanks, Stefan, for the question. So this year, our total propellant flow rate is about 7 kilograms per second. So that's about 4 times what we had last year. So this engine is roughly 4 times bigger, 4 times the injector holes, 4 times the chamber volume. I'm actually not sure if that's linear. Here, let's see. I'm looking around. I don't know actually if the igniters are over here. Sorry. All right, I don't know where the igniters went, but they used to be over here. Awesome, BPS Space, go NASA, thanks for that. I've watched a lot of BPS Space videos. They're really sweet with the control surfaces that you have on the small rocket and being able to land it back down. That's awesome. So here we are at Mission Control. Hardly working, or working hardly. How's it going, Alex? So where are we in the process?
They are currently filling the LOX tank with LN2 to chill in the system, and we are monitoring thermocouple pressure data and actuating tests.
Awesome, thank you. This is the computer that will be streaming video for ourselves. So we're gonna have 4 GoPros inside the bunker streaming video. So yeah. Can you click on the link? Make sure it works. Is it link for the print? All right, ask more questions if you have them. I'm happy to answer them and tell you guys how our stuff works. So if you guys think of any questions, definitely leave a comment, and I'm reading the comments, by the way, so I can answer your questions. All right, let's go. Okay, so how are you using simulations in your design and analysis workflow? Yeah, so simulations are a huge part of what we do. So you can't just design something in SolidWorks and be like, yeah, that looks good, let's build it and test it. What you have to do is you have to, once you do design in SolidWorks or your 3D modeling program of choice, you have to do analysis on it, make sure it won't break, or basically it won't break. There's a lot of ways things can break. Maybe if you're applying too much load onto your component, it'll fail. But also if your component is going through a thermal gradient, if one side is 500 degrees hotter than the other side,
you'll actually get a stress induced from that temperature difference, that temperature gradient, and that can actually break your part. So we use ANSYS FEA to do our analysis. ANSYS, that's the name of the program. And actually, our analysis has shown a lot of interesting things this year. So the first version of the engine that we designed, that we had in SolidWorks, it actually wouldn't have worked. It would have blown up like 10 times over. There were so many ways it would have broken, and we found those by doing ANSYS. So we found that like the thermal gradient would have destroyed it, the pressure force would have destroyed it, and like a lot of the bolts would have ripped out. There are so many things that we discovered that was wrong with it. So by you doing ANSYS FEA, we find many things to fix with the design, and that's necessary. It's almost impossible to just design something and it'll work on the first try. Like unless you're just like awesome at engineering and you've been an engineer for 50 years, it's pretty hard to design something and have it work with your first design. So we do analysis to figure out what's wrong with the design and then fix it, and also optimize things for mass. We use ANSYS to take a component like say a tank end cap. We want to make it lighter. We put it in ANSYS and see where the stress is on the end cap, and then we know where we can take material away on the end cap. Oh yeah, this shirt is from IREC. Yes, I was at IREC 2017. We launched our hybrid rocket. We launched the hybrid rocket to 30,000 feet, and we won the competition, the overall category. And yeah, this is where I got that shirt. That's good attention to detail. Oh yes, so the LOX lines are they are insulated. You can see here. Let's go over here on the fill system. All the cryogenic lines are insulated because we don't want them to be losing any liquid. So basically, we got these ones down here, coming up here. Those are all liquid oxygen lines or liquid nitrogen lines. I'm not sure. Yeah, I think. So we got that one going into the bunker. And so we have this one going into the bunker. And then that one going into the bunker. Into the hole. So one of those is LOX, one of those is LN2. I'm not sure which one. And yes, they are insulated because if they're not, then basically the heat from the air just heats up the Hey guys, sorry about that. I guess the stream decided to cut out. I also just realized that I have a front-facing camera. I don't need to turn my phone around to talk to you guys. So I'll use the front-facing camera for that. Let's see. All right. So this is where we left off. I didn't lose any, guys. Let's see. Oh, okay, another question. How do you do CFD simulations as well as FEA? Great question. So we use CFD to do fluid simulation. We don't do as much CFD as we do FEA. There's about probably a 10-to-1 ratio of like structural simulations we do in ANSYS versus fluid simulations we do in a CFD program. I think we also use ANSYS for CFD, but we do way more like structural analysis. So there are a few things that we do ANSYS for, like the injector design. The injector is a tricky thing that we have to do fluid simulations for. We also, I think we have done some fluid simulations on our propellant valves, like trying to see what the pressure drop across them will be. So let's take a look inside the bunker and see what's going on.
On the tank where it's full, so I can it's like the fill level.
I mean, the tank also can fill itself in a way. Like the outside now is going to take a lot longer to fill than the inside now, so we have really no idea. The bunker's getting colder for sure.
Like I feel colder. I think that just might be some leverage.
Actually, that gap is not that cold.
Yeah, so I can tell that the line here is fully filled.
You have a fully filled and flowing liquid or two different things.
Yeah.
I'm pretty sure.
Right now, I think what's happening is it's killing the Ethanol.
Yeah,
I think.
we really suffer a lot from this way itself.
Yeah, I think what we can do is if we get some extra insulation like that foam there, wrap it around here, because right now it's backing up the pin.
Yeah.
Like, it's probably minor, but because we're like operating on pretty low LNG, we're gonna want to change everything.
Yeah, I really think that blowing our cold air upwards is probably hurting us a lot.
Yeah, possibly. I think really in the future, this won't be that. Well, I don't know.
We need to put it in the future now.
The thing is, you want to go to the main line eventually.
Yeah.
So you don't want to diffuse there.
Why don't you want to diffuse on the take the main line?
Yeah.
Oh, into like the rocket?
Yeah.
Oh, we can worry about that problem later. If you
Yeah.
can't get fluid in the tank now, that's a problem.
We also have to worry about flowing out.
Yeah, but Do you want to log this in the background?
Yes, the answer is we do almost all of our machining in-house. I would say 90% of the components are machined in-house because we have a great machine shop and a great group of machinists. But there are some things that we cannot machine in-house, like the injector plate. The injector plate has about 250 holes on it. They're all angled. So we had that machined out of house. That costs about $1,000 to make out of house. But other things like the injector manifold, which distributes the fluid over on top of the injector plate, we machined that in-house. And also, another thing that we didn't machine in-house is the graphite nozzle. Graphite is a huge pain to machine. It's dirty. It's hazardous too. Like the dust and the graphite gets everywhere. It like gets into the air and you breathe it in. You need to wear face masks when you're machining graphite. Also, it's electrically charged when you machine that. So what happens is the graphite dust when you're machining will like get stuck to components on the lathe, for example, and you can actually break your lathe by machining graphite. So we don't machine it in-house anymore. We used to, and then people got mad at us for machining it. So we only do graphite components out of house now. We have a certain shop, Graphite Machining Incorporated. They're actually our sponsor, and so Graphite Machining Incorporated machines that for us, and they supply the material for us. So thank you, Graphite Machining. What was the total budget or estimated cost for the rocket build? So I'll talk about last year's rocket build. This is Ethan. Ethan helped on the rocket build last year. The two of us worked a lot on the propulsion last year. So last year for our 1,000 pound force liquid engine with the tanks and plumbing and all of that, that was about $20,000 to develop the whole system and build it. The actual hardware on the engine only cost maybe $3,000, right?
Yeah, that's
like raw materials and the solenoids and the components on the engine, about $3,000, but it's just $20,000 to develop it, like build other versions of the hardware.
Yeah.
And the most expensive part is development.
Yeah, most of your costs come from development, or at least with this sort of thing. It's especially when we're pumping up the complexity. Things get a lot tougher.
Yeah, like maybe the cost. So for this, we're competing the Base 11 Space Challenge to send the liquid rocket to space. The cost of the rocket itself, when we actually go to build it, it'll maybe be $50,000 to $60,000, right?
That sounds about it.
But the development of this, like building test engines, building test hardware that will never fly, buying software, like just buying hotels at the competition, like logistic costs, like buying U-Haul trucks to haul stuff out to our site. That's what really brings up the cost of the development. So overall, it might be $250,000, even $350,000 to do this whole program over the course of 2 to 3 years. So
Yeah.
all right.
You want to do a run through the hardware?
Yeah. All right. So now that we don't have the venting anymore and it's not super loud, we can check out the hardware and have Ethan explain what's going on.
Yeah, so here you can see the engine mounted in the test stand. It's mounted on some linear bearings, just some ease of access. Right now it's sort of like clamped into place so it won't move too much. Yeah, so this is a 3,300 pound thrust engine, LOX ethanol. You can see we have a regen manifold there for active cooling. The outside is aluminum. A lot of people, they see, they're like, oh, it's made out of aluminum. You sure that's not going to melt? There's a few other things going on. So this is a heat sink nozzle for short duration things. You don't really need a fully developed nozzle to do some short duration tests. You can do. You can see here the main propellant lines, just for the cold flow here.
They don't look pretty.
Yeah,
we made them jank just for this because we were crunched on time. Yesterday we had about an hour to put it together, so we were like, oh shoot, we need to get some flex hose. It looks pretty bad. It looks pretty gross. We have a concoction of NPT fittings and flex hoses, but it won't be like that for the next for the hot fire. It'll look a lot prettier for that.
Yeah, so there'll be this will be a lot more uniform. It'll probably be just one connection there. And then you can see our tank stand and so-called rocket panel. We pride ourselves in trying to build pretty much everything we possibly can in-house. These tanks were made in-house, the tank stand made in-house. The main propellant valves.
Let's check out the fuel tank up here. So that's kind of what the tank looks like. That's just for hot fire tests. That's not what the tank in the rocket will look like. This is the liquid oxygen tank. It's welded. It's a little bit taller. It's behind some insulation.
So you can see John's working on installing some extra insulation on our hardware there. That's mostly because the LN2 for our chill process.
Yeah. So what's this big dewar doing over here? What are we doing with this dewar, and why is it connected to the tank?
Yeah. So liquid oxygen is a cryogenic fluid, so that means it needs to be very cold in order to be liquid. So basically, we're chilling the tank. We're not going to be using any oxygen today, but we're sort of replicating our process for when we do use oxygen. Right now, this is sort of an intermediate setup because we had to overcome some problems with the fill system. But basically, this LN2 tank, liquid nitrogen tank, is being used to chill the hardware, bring it down to the cryogenic temperatures so that...
So this is the liquid nitrogen tank, and then over here is the liquid oxygen tank. We are filling it with liquid nitrogen to chill it.
Once this stuff is cold, then we can do our fill, and we'll basically be starting the actual cold flow process then, and that'll be all conducted from mission control.
Awesome. And someone just asked what fuel we're using, and then Gabe said 75% ethanol. That's wrong. We're not using 75%. We are using 95% anhydrous. Is it anhydrous?
Yeah, we're going to be using anhydrous here.
Yeah, 95% anhydrous ethanol for the fuel.
Yeah. Repeat that.
Distilled 265.
Thermocouples don't off.
All right.
That sounds good.
We haven't actually confirmed that that's...
Yeah, but everything else.
The other one's accurate.
Everything else is pretty on par.
Okay.
Also, our tank pressure right now is 12%, 12 psi.
Go ahead and open the vent. Open, confirm. That's not great, but it's good. That's fine. Careful getting out of there. John, if you can head back there,
I don't like either of those numbers.
Okay.
So, trying to think, hold on, up and down, couple, 285, 290, 71, 71, which means that, like, it's 50 degrees outside, 47
that with the gas that's created in there, there's a lot of mixing. So the actual transient of the actual location across the tank is not it's not just a linear it gets colder and it goes up. It's not
The metal acts
forward.
The metal acts like that. The metal is not immune to transient, but it's just a lot to heat up the metal. I mean that it's gonna have a pretty good transient.
Yeah, it should be like that, but while it's venting, there's different flows going on in there. So I bet you the top of that tank is colder than the middle of the tank.
Yeah. Then it's in the Celsius down.
Yeah.
That's pretty good light.
Yeah, that's not ideal. That's pretty much, that means the pressure in that tank is 12 psi.
Yeah. So, Cameron, can we hook up the lock door, cold LN2 right now to this and use it as a music?
Yeah. Good. Show it. Is that pressure not low enough, or is that not high enough? What?
Okay, 12.
12?
Okay, yeah.
You could the other one has a good 22 in it.
I think honestly, I know you were talking about the transient with the pressing it with nitrogen, but it will force more liquid out, so that might be what we need.
Yeah, maybe.
So that might be an option.
Yeah. We could also, yeah, that might be best if you just want to get a line over to it.
Yeah. So
From the helium?
no, not helium. We have to transport small. We have a nitrogen tank that's at 50 psi already.
Yeah.
So if we don't have a welding regulator or something, we can just
We can take the one that has high pressure and just put the regulator on top of it.
that would be better. If we can have it. So if we can get a convoy to do that, or just
It has to be done in the U-Haul.
okay.
To go get hardware?
Yeah.
Okay.
So I think we'll need that. We're gonna keep operating like this, but
Wait, so what do you need? You need the nitrogen bottle?
yeah, we need a nitrogen
On
bottle.
that. It has a regulator attached to it.
Is there one?
Does it have the ox? We want the ox one actually, right? The ox regulator.
I mean, this is all clean for
I
us.
don't have an option regulator.
No, listen. The silver regulator.
Yeah.
We need that one.
It's on the tank right now.
You sure?
Yeah.
Okay.
Is the bending the black stuff on it?
You know the regulator used for cleaning?
It's in the wet lab attached to the tank you need.
We need that regulator.
So just the tank with the stuff that's on it,
Yeah.
and nothing else.
Yeah. If for some reason the tank doesn't have the regulator on it, we do need the regulator.
So
It's on there.
you don't need any of the fittings or anything. That's all you need.
Well, this is British NBC. What am I
We
looking
have all the
at?
fittings here.
Okay.
This 3/8?
No, we can use the gas vent if we need to.
The one got 3/8.
Yeah, that's true.
Cameron,
Oh.
get the filter on the table.
The filter on the table? Where?
Remember that filter we were talking about? Where did that go?
Maybe you should go back. We're not going to do any other operation, so I can operate this. I think that would be fine. While you guys take care of that, I'll continue with this plan.
Oh, by the way, this is our igniter. So you can see the E wire, the E matches right here. On the inside of this is the APCP chunk. I was talking about that earlier on the live stream. Wait, do one of you guys want to come with me? Or
This one is starting to fill in.
should I just grab Paige to come with me?
Okay, you'll know exactly what we're talking about.
Okay.
If you have any questions, call.
I'm gonna take the live stream with me.
Okay.
All right. Okay, so an update. We actually have to go get some hardware from our workspace. The problem that we're having is the liquid nitrogen doer is very low pressure. It's only 10 psi right now. We want it to get up to 20, so we can force in more liquid faster. So we're actually going to go to our workspace, get a nitrogen bottle with a regulator on it. So you guys can actually come with us. Hey Paige, you want to come with me to workspace when you get a bottle? Cool. All right, you guys will follow us through the workspace. we're gonna go get a nitrogen bottle. You can see our wet lab space in the works where we build our hardware. All right. Do you want to do the live stream? You want to hold it?
Yeah, I can hold it.
Oh no. I can't use a key properly. There we go. Rusty. It's a little bit rusty. Oh, the struggle that we have to go through to build rockets. This section kind of stuck. Oh my god. Let's see how it works. There we go. Good. Got the door open. What's harder, firing a rocket engine or opening the door of a U-Haul?
Before proceeding, release the parking brake.
Okay, so oh, we got a really smart brake. I guess while we have the opportunity, we could talk a little bit about you know, some of the stuff we do in the workspace. So Paige, what do we do in our workspace and our wet lab?
Oh, in our wet lab, that's where we go through our cleaning procedures in order to make sure that all of our components are clean for liquid oxygen service.
Awesome. What do we do to prepare something for oxygen service? Yes.
So the process that we go through has multiple steps. The first thing that we'll do is just scrub the components to make sure that they're visibly clean, so that there's no visible debris or oils on there. You want to make sure that you have gloves on the entire time because the oils from your hands actually can contaminate your components.
Yeah.
So
also, you can hit the button to face forward. So if you want to talk about how to clean components.
yeah, so the oils from your hands can contaminate the components. After the components are visually clean, they're still not clean. So we need to go to the next level of cleanliness, which is our industrial cleaner blue gold solution, which we put all of our components into a ultrasonic bath with our blue gold solution, and that'll help get rid of any additional oils that are on there. After that, we will rinse with running water to remove the cleaner, because if the cleaner dries on there, it then becomes a contaminant. Then we will soak all of our components in a deionized water, and lastly dry with gaseous nitrogen, inspecting the entire time to make sure that there are no contaminants, no pieces of Teflon tape, anything in there that could become a particle or cause issues for liquid oxygen.
How many components do we have to clean on the entire fill system? Like 500 or something?
Something like that, yeah. And before we move on to our next hot fire, we're going to have to go and re-clean a lot of the components.
Did we get them dirty?
Yeah. The
That's
tank
unfortunate.
stand.
Oh yes, tank stand. Yeah, we'd like to think that we can just clean all the oxygen components, build the fill system, and then never touch it again, like never have to clean it again, but sometimes we screw up and we actually get some of the lines contaminated, so we have to re-clean those lines.
Right.
Yeah. So yeah, we are going to the Wilson Center. So our test site is at is a little bit outside of campus. We're going back to campus. We're almost there, and going to our workspace. So we operate in the Wilson Center building. That's where all like the project teams, like Baja, Solar Car, MFly, that's where all the teams operate. Us as well. So we're going in there. We have to grab some nitrogen, and then we'll be going back. So it's funny. You might think for a hot fire and a cold flow, we show up, we plug in all our hardware, and then we fire the engine. That's not how it goes. What happens is it's a back and forth running and getting more hardware. Like, oh, we forgot something. Oh, there's an issue with you know, there's an issue with the igniter, there's an issue with the avionics, so it's always problem solving, working through things, trying to, you know, find solutions to these weird problems we're running into for the first time. So it's not as quick as just plugging in all the hardware and turning it on and then firing the engine. It's a pretty complicated process. Usually these are all-day events or even all-weekend events. You know, we started yesterday. Now it's Sunday, and we're working hard trying to get this to happen. All right, we're almost here at the Wilson Center. You guys probably didn't think this engine hot fire cold flow would bring you driving down the road, but it does. You can read some of the questions if you hit the comment, like the little,
Alright.
yeah. So you hit it like twice or hit the screen or something. That way you can see what people are asking. We can answer them.
I had to get, what safety factor do you use on the propellant tanks in the combustion chamber?
Oh yeah, so that's a good question. Usually we go with like a safety factor of 2.
Release the parking brake.
But sometimes we go down to like a safety factor of 1.5. Sometimes we're like safety factor 4 even on like more important components. But yeah. All right. This is the Wilson Center. Here we are. Swipe in. Oh yeah, here. Hold it. Okay. Do we have a dolly?
There might be.
Sorry?
There might be one somewhere. So this is our wet lab. This is where we do our liquid oxygen cleaning procedures. Here we have some of our things set up right now.
Alright, so this is this is what we want. We're gonna take all the plumbing with it. But we need a dolly, so let's go grab that. This is where we do some of our machining stuff. This is pasta machining. We've got manual machines in there. Well, there's no dollies. Oh shoot.
It's not at the bunker, is it?
Could be. Wait, I think we have a dolly in. Do we have a dolly in a U-Haul?
Maybe.
Okay, let's go check. Let's check the U-Haul for a dolly. Or let's just see if there's any hanging around. Did we really? Oh shoot! Wait, did we take the dolly? Like for the gas cylinders, it belongs to. Oh, here's one. Here's one. We found it. Yes. Oh, we need to go to the wet lab. Wrong direction. Hello. I did. Here, you just wanna, I'll get it hooked up. You just wanna talk about, show some of the stuff that.
All right.
Cleaning hardware.
So this is our space in our wet lab. This is where we'll keep components before we start cleaning them, and after they're done cleaned, they'll be put in clean room bags, which are specially cleaned and free of any contaminants that you might see in normal plastic bags. But here's our ultrasonic with our Blue Gold solution. Blue Gold is an industrial cleaner, and I don't know why it's called that. I get that question a lot, apparently.
why it's called blue gold,
Yeah.
and we don't know.
But we have lint-free cloths because when drying or setting the components down on paper towels or any normal cloths, they will tear particles off and again become another contaminant.
Okay. There's our nitrogen tank that we needed.
Yeah, the University of Michigan, really big facility. We're a college team. We get to use college facilities. Cap.
There we go.
It's dangerous.
What?
You can't transport it with the regulator on.
Regular off?
Yeah.
All right. Maybe just the injector. You can show off the injector.
Oh, this is our hydrostatic plate for our injector. So in order to help test the seals, the seals around the injector, we actually have a bottom plate without any holes in it. So it won't be mixing any of the fluids, but it allows us to test for leaks and see what kind of issues we'll have with sealing. So with the cylinders, it can be very dangerous to transport them without any, with regulators on and without a cap on it. So we want to make sure that we follow the protocol necessary. And right now Cameron's looking for wrenches. Oh, here we have our PPE procedure to make sure that all of our students who are involved in cleaning not only stay safe and keep our parts clean, but so that we can replicate it every time accurately and without issues. But this is the Wilson Center student lab for the University of Michigan. There's lots of machines here, and we do a lot of our own machining for our parts. We have different sub-teams that will work on different procedures and different tasks for the rocket.
I think what we'll do is probably pause the stream for a minute while we get back to the test site so we can go quicker, and then resume in like 20 minutes probably.
All right.
Okay, so 1 second. So yeah, I'll pause the stream, probably be back in 20 minutes. All right, thanks.